Hello and welcome once again to the Aakash Byju's YouTube channel. My name is Atiullah and we are live yet again with another interesting session, this time on JEE Mission 2022. So before we begin, just let me know if you can hear me properly and you can see me just right. Alright, give me a thumbs up, give me a yes, just let me know if you can do that so that we can proceed with this session. Alright, Nabil, hello, how are you? Kamal, how is it going? Captain Jack Sparrow. Hello Sifa. Alright, how are you guys? Good evening, Hilda. How are you? Alright, familiar faces. It's good to see familiar faces, or I should say familiar usernames. Most of you don't have the real name over here. That's fine. Good to see you guys. Very happy that you are attending all these sessions very regularly. That's great to see, and I hope this sessions that we are doing is helping you. All right, okay, so if you can hear me, give me a yes. If you can see me right, give me a thumbs up. All right, yes, everyone can see me and hear me. All right, let's get started with this session. So if you have been following us, we have been doing this session where the objective is to do revision. And how do we effectively do revision is by solving questions. Alright, so you know the drill. What are we going to do? We have a set of very good questions that we have picked, and the topic for today's session is electrostatics, Gauss's law and capacitors. Alright, a very important topic of class 12, a very important topic from JEE standpoint. And the interesting thing about this topic is whatever concepts you learn here, you can later apply those concepts, very similar concepts in magnetism and other chapters. Alright, hello Suzanne, good evening. Alright, hello Wes. Welcome guys. So you know the drill. What are we going to do? I'm going to throw a question at you. You should be ready with your pen and notebook. And the first thing you're going to tell me is what are the concepts that is going to be applied in this question in order to solve it. And once we have done that, when we have discussed that, then we're going to solve it together. Alright, so with that said, we are going to start very shortly. Pratyush, namaste. Shamun, hi. Aniket, hello. Good evening. Good evening, Swastika. I think Swastika has been the most consistent person attending all these sessions, so kudos to you, great job. Yes, let's start. Alright, so if you're ready, I'm throwing the first question at you. Alright, what is the first question? Let there be a symmetrical charge distribution with charge density varying as rho r is equal to rho naught into 5 by 4 minus r upon capital R up to small r is equal to capital R, rho r is equal to 0 for r greater than capital R, where small r is the distance from the origin. Okay, the electric field at a distance r, which is less than the radius from the origin, is. Okay, so I hope this question is clear to you. So what we have here is we have a symmetrical charge distribution. So you can see that it's spherical symmetry, and then the charge density is not constant. It is a function of the distance from the center. Okay, and it is given by this function. Okay, so this charge density is within this region. Okay, what is this region? This region is small r less than capital R, and for small r greater than r it is 0, which means outside of this there is no charge. Okay, so that is the question. We have to find out the electric field at a point which is at a distance r from the center. Alright, so the first thing you're going to tell me is what is the concept that we are going to use over here. Alright, quickly tell me the concept that I need to use in order to solve this question. What do you think is the concept that we should use over here? Alright, and together what we're going to do is we are going to create a concept checklist like we did the last time. Okay, so whatever concepts we are discussing, and I'm going to tell you what are the related concepts. So we are going to note, you are going to note that down in your notebook. and you're going to later see that if all the concepts are clear to you or not. If there is any concept that is not clear to you, you're going to pay some extra attention to that. All right, so we are going to, sir, we'll have to integrate. OVAS, you are absolutely right, we'll have to integrate, but the thing we asked here was what is the concept we are going to use. Absolutely, Sujay, we are going to use Gauss's law. Suzanne, yes, we are going to use Gauss's law. Okay, so what does Gauss's law say? Gauss's law says that the closed integral of E dot ds is equal to q inside upon epsilon naught. Alright, this is Gauss's law. So if we choose a Gaussian surface, we calculate the flux of the electric field through this closed surface, then that is going to be equal to q inside upon epsilon naught. Alright, this is Gauss's law. Now you tell me that if we have a situation where the charge is symmetrical and it is a spherical symmetry, then what is the shape of Gaussian surface that we should choose? Alright, so Gauss's law is very, very simple, but it is only effective if we are able to choose the correct Gaussian surface for the given charge distribution. So can you tell me what is the charge distribution we should, what is the shape of the Gaussian surface we should use? Absolutely. So the symmetry is spherical, so the Gaussian surface should also be a sphere. Alright, so what we're going to do here is we're going to take a Gaussian surface like this. Alright, so we are going to choose a spherical Gaussian surface like this because we have to calculate the electric field at a distance r from the center. Okay, now what is the argument? Because the situation is symmetrical, then the electric field at all the points will have the same magnitude. Do you agree? The electric field at all the points on this sphere is going to have the same magnitude and they are going to be perpendicular to the surface. Do you agree to that as well? Okay, is that correct? What are the two things we are saying here? Because the situation is symmetrical, the magnitude of electric field at all these points is going to be the same, and second, the electric field is going to be perpendicular to the surface. Okay, we have done this many times. Alright, so if we have to do closed integral of E dot ds, then what will happen? Because we can write it as closed integral of E ds cos theta. Okay, what is E ds cos theta? Cos theta is the angle between the area vector and the electric field. Is that correct? So since the magnitude of electric field is constant, we can take that out. Cos theta, at every point the electric field is normal to the surface. Okay, which means that the angle between the area vector and electric field is going to be 0 degree. Okay, how is the area vector? The area vector is perpendicular to the surface. Do you agree? The area vector here is going to be perpendicular to the surface, which means it is going to be parallel to the electric field. So what is the angle between the electric field and area vector? It is 0 degree. So cos 0 is going to become 1. So E comes out and we have the closed integral of ds, correct? So closed integral of ds means you have to take the, if we integrate that, we are going to get the total area. ds is the small area. If we integrate that, we are going to get the total area. So what is the area of the sphere? The area of the sphere we know very well is 4 pi r square. Alright, I hope the LHS is clear. Now if the LHS is clear, what is the RHS? The RHS is q inside upon epsilon naught. So what do we need to do? We need to find out what is the charge inside this Gaussian surface. Do you agree? Okay. Sujay is asking, is E is constant? Sujay, E is only constant in magnitude, it is not constant in direction. Okay, perfect. Alright, so what is our job? Our job is to find out what is the charge enclosed. Okay, the charge enclosed inside this Gaussian surface. Is that correct? Sujay is asking, sir, is E constant here? The magnitude of electric field is constant, not the direction. Okay, the direction is going to be changing at every point, but the magnitude is constant. Alright, so our job now is to find out what is the charge enclosed inside. Okay, now finding out the charge would have been simple. What would have been the charge? The charge would have been the density, the charge density multiplied by the volume. But the problem here is that the charge density is not same. Okay, so as someone said, we have to integrate it. Okay, so we'll have to break this entire region, break this entire volume into small regions and find out what is the total charge. Okay, how do we do that? Let's do it like this. Okay, so what I'm going to do is, at a distance x from the center, I'm going to take a thin spherical shell. Okay, and this thin spherical shell has a thickness, how much? You can guess that. It has a thickness of dx. Is that correct? Okay, so this at a distance x, which means this thin spherical shell has a radius x and it has a thickness of dx. Now can we calculate what is the volume of this particular region that we have chosen? Okay, for this thin concentric spherical shell, what is the volume? Okay, the volume is going to be dV is equal to, okay, how do we find this volume? So what we are going to do is, we are going to cut open the sphere. Okay, we are going to cut open this sphere and flatten out. Okay, so this is a sphere which has some thickness. We are going to cut open the sphere and we are going to flatten it out. Okay, now if we are going to flatten it out, what is going to happen? If we flatten it out, then whatever be the shape, not important, whatever be the shape, then the surface area would be like this. This will be the surface area. And then what will be there? There will be a thickness. Okay, there will be a thickness. And how much will be the thickness? The thickness is going to be dx. Think about it. Okay, you cut open a sphere and lay it down flat on the ground. So this is going to become a surface area and it will have some thickness. Okay, so what is the surface area of the sphere? The surface area of the sphere is 4 pi x square, because the sphere has a radius of x. Okay, so the surface area is going to become 4 pi x square, and then in order to find the volume, we have to multiply it by the thickness. So we'll have to multiply it by dx. Okay, so I see a few answers over here, but the answers I think are not absolutely correct. So Swastika is asking, we have to integrate the density function. No, Swastika, what is the objective? The objective is to find out the charge. Okay, the objective is to find out the total charge. So what we are going to do is, we are going to divide this in small regions. Okay, we are going to divide this in small regions. We are going to find the charge in that small region and then integrate to find the total charge. Okay, that is what we are going to do. Okay, Jack Sparrow is asking me to explain it again. No worries. Okay, we are going to explain it again. I know it's not a very straightforward concept, so nothing to worry. What we have done is, this entire sphere, okay, what is it? It is a sphere. It is a solid ball. Okay, it is, let's say, a deuce ball. Okay, it is a solid ball. Everything is solid. There is no hollow inside. Okay, it's a solid ball. So can we say this solid ball is made up of thin shells? Can we say that? Okay, so we take a Costco ball and we put another Costco ball on top of it, and we put another Costco ball on top of it. So what we are going to get? We are going to get a solid sphere. So we can say that this solid sphere is made up of many concentric thin shells. Do you agree? Okay, so this is one concentric thin shell that I have chosen. So it has a radius of x and it has a thickness of dx. Okay, now I want to find the volume of this thin shell. I want to find the volume of this thin shell. Now think about it. Let's say this is my hand, and my hand is a thin shell. Okay, it is a thin shell. So you can see it's hollow inside. Okay, it's not a solid inside, it's hollow inside. So it is a thin shell. Okay, now what I'm going to do is, I'm going to cut open it and I'm going to place it flat on the table. Can you see that? This is a shell, this is a shell. I've cut it open and I'm going to lay it flat on this. Okay, so whatever was the surface area of this sphere, when I lay it out flat, isn't that going to be the surface area of this region? Do you agree? So the surface area of the sphere is the same as the surface area when I have laid down flat on the table. Okay, and whatever was the thickness, of this sphere, that is the thickness of this particular shape. Okay, this is going to become the thickness. So if I have to find the volume, what do I have to do? I have to take the surface area and I have to multiply it by the volume. Is that correct? Okay, so this is the surface area and I have to multiply it by the volume. So what is the surface area? The surface area is 4 pi x square, the surface area of the sphere. That is going to be the surface area of the flat surface also. So 4 pi x square multiplied by the thickness. So 4 pi x square dx. Is that correct? Alright, so this is something which is extremely important to understand, because this is a method of integration and this comes at a lot of places. Okay, finding the approximate volume or finding the approximate area, this happens in a lot of places. Okay, so if you have understood this, let me know so that we can proceed. I know it's not a very straightforward concept, but nothing we can't handle. All right, so the volume of this thin spherical shell, okay, the volume of this thin spherical shell is 4 pi x square dx. Okay, now in this region, what is the charge density? Okay, in this region, what is the charge density? So it is at a distance x from the center. Okay, it is at a distance x from the center. And what is the charge density? The charge density is rho naught into 5 by 4 minus small r upon capital R. So what is small r? Small r is the distance from the center. What is the distance from the center here? The distance from the center here is x, which means the density here, the charge density is going to become rho naught into 5 by 4 minus x upon capital R. Okay. Is that correct? Okay, this is going to be the density for this region only, because this region is at a distance of x. Okay, is that correct? So can I say what is the small amount of charge? The small amount of charge in this region is going to be rho dV. Do you agree? The small amount of charge is going to be the charge density multiplied by the volume. So the charge density is rho naught into 5 by 4 minus x upon r, and then we have dV, which is 4 pi x square into dx. Okay, now if we have to find out what is the charge, then what do we need to do? The charge here is going to become the integral of this quantity. Do you agree? It is going to become the integral of this quantity. So what I'm going to do is I'm going to take out all the constant terms and keep the variable terms inside the integral. Okay, so rho naught into 4 pi, these are all constant terms, and then inside we'll have 5 by 4 x square dx, and then we are going to get minus of integral of this is going to become x cube upon r. Is that correct? Now if this is correct, we have to put the limits. Okay, now think about the limits. So I have to find out what is the charge within what region? Within this region. Okay, within this region. So for this region, the radius has to go from 0 to small r. Do you agree? If 0 is here, then what is small r? Small r is going to give me this spherical shell. So this is going to go from 0 to small r. This is going to go from 0 to small r. Is that correct? I forgot dx in the second integral. Absolutely, that's very foolish of me to do that. Alright, but it's back. Okay, so let's do this integral very quickly. It's not difficult at all. So I'm going to write it over here. Oh, I am a little short of space. So let me rub a few things from the top. You can always go back to this video and copy if you want, but I want some space. Alright, so this is going to become rho naught into 4 pi, and then we have 5 by 4 over here. So x square dx, the integral of x square dx is going to be how much? It is going to be x cube by 3, and the limit of integration is 0 to r. So this is simply going to become r cube upon 3 minus x cube dx. Okay, x cube dx is going to be x to the power 4 upon 4. Okay, and when we put the limits, it is going to become r to the power 4 upon 4. This constant term is going to be here. So this is it. Okay, yes, we have done that. Okay, is this clear? Is the integral clear? Alright, so this becomes the charge inside. Do you agree? This becomes the charge inside. So now what I'm going to do is I'm going to rub this off again to make some space. Really a space crunch over here. Okay, never mind. So we have calculated what is the charge enclosed. So E into 4 pi r square. Now go back to our original equation. E into 4 pi r square. That was the closed integral of E dot ds. And this should be equal to rho naught into 4 pi. And then we can take out the constant terms. Okay, so we can take out r cube. We can take out r cube. and then we can take out 4 from the denominator. So this is going to become what? This is going to become 5 by 3 minus R upon capital R. Do you agree? All right. So what do we have? We have 4 pi and 4 pi gone, and then this R square and this gone. So we have E is equal to rho naught R upon 4, and then we have 5 by 3 minus R upon capital R, and that should be my answer. Is that clear? Let me know if this is clear to you, or do you have any confusion regarding this. So what will be the correct option? Correct option is going to be option C. Okay. So we saw what was the basic concept behind this question. The basic concept was the Gauss. Basic concept was Gauss's law. Okay. But the really challenging part here was the integration. Okay. So someone just said, Azim said that it's a little bulky. Okay, I agree. This question is a little bulky, but the thing is that with enough practice, okay, if you are comfortable with integration, this should not take a lot of time, because we had to explain everything. I had to write everything down. That is why this became very bulky. That became a question which we had to solve in so many steps. But if you are comfortable with integration, then you can write the integral in one step. Okay, you can write dv, you can write dv into rho in one step and integrate it in the next step. Okay, so all it requires is a little bit of practice, but I would say this is a little lengthy, but nothing that you can't expect. Okay, you can expect this kind of question because this is a question which has come in JEE Main. So we have to be ready for that. Okay, it's not always going to be easy, but we have to do enough practice so that integration doesn't bother us. Okay. All right, perfect. So this question is done. I hope this is clear. All right, so yeah, Jack Sparrow reminded me that we had done this last time. Okay, what had we done? We had done a rating, a difficulty level rating of the question. Okay, so you can do that. Absolutely, that gives us confidence. That gives us an idea what should we be prepared for. Okay, so do give your rating. Okay, from where did that epsilon naught come? Epsilon naught, sigma upon epsilon. So this is Q upon epsilon naught. All right, so my bad over here. So this charge we have calculated. So this charge we'll have to divide it by epsilon naught. I'm sorry, I missed that. So this charge we'll have to divide by epsilon naught. That is why we are going to get epsilon naught. Okay. Closed integral of E dot ds is equal to Q inside upon epsilon naught. All right. So yeah, it was average difficulty level question. Nothing we can't handle. All right. Now let's get to the next question. All right. So what do we have here? We have two charges equal to Q. They are placed over here at minus A and A on the x-axis. And then we have a mass m, and it has a charge Q naught is equal to Q by 2. Okay, so this charge over here has a charge Q by 2. Now it is placed at origin. Now if the charge Q naught is given a small displacement y much less than a along the y-axis, so it has been given a displacement of y which is much less than a, then the net force acting on the particle is proportional to. Alright, so we have these options. The first thing you're going to tell me is what is the concept we are going to use. Tell me the concept. Is the question clear? We have to find out what is the net force. Okay, the net force is proportional to, or what is the relationship between this displacement y and the net force. That's what we need to find out. Okay. All right. So what is the concept we are going to use over here? Coulomb force between charges. Yes, it's a simple concept we are going to use. Absolutely, Azim. It's a very simple concept we are going to use. Coulomb's law. We know that, and we also know that in order to find the net force, we need to add up all the forces that are acting, and It has to be done vectorially. Okay, that's about it in this question. All right, so this is why. So the force on this particle is going to be like this. Okay, so due to this charge, the force is going to be like this. Do you agree? And due to this charge, the force is going to be like this. Do you agree? And we can say that it is symmetrical, so the magnitude of both the forces is going to be the same. Is that correct? Okay, so magnitude of both the forces is going to be the same. So let's quickly calculate what is the magnitude of this force. Okay, so force, what is Coulomb's law? Coulomb's law tells me that this is K into Q1 Q2 upon R square. Alright, where K is 1 by 4 pi epsilon naught. We know this very well. So I want to calculate what is the magnitude of this force. So this becomes K, and the charge is going to become Q into, and the value of Q naught is Q by 2. So Q1, Q2 I have written, and that divided by R square. Okay. Now what is the distance? This is the distance. This is the distance between the charges. Now this is A, and this distance is Y. So very easily we can say that this distance is going to be A square plus Y square under root. Is that correct? So this is R. Can we say this is R? So if we know this is R, all we have to do is square it. So this is going to become A square plus Y square. So this becomes KQ square upon 2 A square plus Y square. Is that correct? Okay, so we have calculated the magnitude of force, but is that enough? No, that is not enough, because we have a force over here, we have a force over here, and then what we need to do is we need to add these two forces vectorially. And if we have to add these two forces vectorially, then we'll have to use a little bit of vectors. Okay, so let's say this angle over here is theta. So this angle over here is also going to become theta, and this angle over here is also going to become theta. Okay, now what we can do is we can take components. So the component in this direction is going to be F cos theta due to one force, and due to the other force also the component is going to be F cos theta. So they're going to get added up and they're going to become 2F cos theta. And then this F sin theta and this F sin theta, we can see, is going to get cancelled out. Do you agree? So what is the net force now? The net force, I'm going to write the net force. The net force now is going to be 2F. So this becomes 2F into cos theta. Do you agree? Is that clear? Okay, so we have found out what is the net force. And do we also know what is the direction of the net force? The net force is in the positive y direction. So I can say this is J cap. The net force is in the positive y direction. Clear? Okay, now all we have to do is substitute and find the answer. Okay, so F net becomes F, which is how much? What did we calculate F as? Let me go back and check. So that is KQ square upon 2A square plus Y square. Okay, now we have to multiply this by cos theta. What was theta? Theta was this angle over here. Okay, so if we look at this triangle, then this is A and this is how much? This is A square plus Y square under root. So from here, can we say cos theta is going to be equal to, this distance is Y, so this becomes Y upon under root of A square plus Y square. Is that correct? Simple trigonometry. Okay, so this is going to become F net is equal to KQ square, here we have a cos theta, so divided by, now I'm substituting cos theta. Now cos theta in the numerator we are going to get Y, and in the denominator it is A square plus Y square under root. So together they are going to make it A square plus Y square to the power 3 by 2. Is that correct? And that is the net force acting on the particle. Now there is an approximation that we have to make as well. We have been given that Y is much less than A. Okay, Y is much less than A. So F net is going to be equal to KQ square Y upon 2. Now this Y is much less than A, so we can neglect Y square with respect to A square. Okay, we can neglect Y square with respect to A square. So this is going to become A square to the power 3 by 2, and that is going to give me A cube. Okay, so what did we find? We found that F net is proportional to Y. Do you agree? That is what we had to find out. So F net, all these terms in the bracket are constant, so F net is proportional to Y. Do you agree? Is this clear to you? Perfect. Now can someone tell me if this is an SHM or not? We have found out F net proportional to Y, which was the displacement. Can someone tell me, is this SHM or not? Alright, SVM says yes, it is an SHM. Alright, I want more answers. What do you think? Is it an SHM? Not an SHM. Alright, Askar says it is not SHM. Swali says it is not SHM. Alright, so because it is a related concept over here, we should discuss that. When we are talking about SHM, then the force should have been negative, proportional to the negative of displacement. Okay, otherwise the particle is never going to come back to the origin, so it is not going to be SHM. Okay, so here the particle is displaced in the positive direction, the net force is also in the positive direction, so the particle is going to go away. Okay, so if F came out to be proportional to minus Y, then it would have been an SHM. So it is not an SHM in case you would have been asked a question. So F we are going to get proportional to Y, so that is going to be my answer. Option A is going to be my answer, and just to discuss it, it's not going to be an SHM. Is that correct? Alright, now quickly rate the question. What do you feel about this question? This is a JEE main question. Captain Jack Sparrow says 2 out of 5. Yes. What do you say about the difficulty level of this question? Azim says 1 out of 5. Excellent. Alright, 2 out of 5, 1 out of 5. Alright, certainly it will fall in the easy category. All we have to do is use Coulomb's law of fundamental force and add them up vectorially. That's all we have done. Okay, perfect. Now let's move to the next question. Are you ready for this one? This might be a little higher in the difficulty level. Alright, let's see. But I'm very hopeful you guys would be able to solve this very quickly. Alright, let's see. What do we have? We have a thin disk of radius b is equal to 2a, and it has a concentric hole of radius a. Can you see that? Okay, now it carries a uniform surface charge sigma on it. If the electric field on its axis at a height h, where h is much less than a, from its center is given as c into h, then the value of c is. Alright, is the question clear? So we have a disk which has a concentric hole inside it. Alright, so the radius of the hole is a, the radius of the disk is b, and it has a uniform surface charge density of sigma. Now h distance above, so you have to think of the axis is going into the plane of the screen. Alright, the axis is going into the plane of the screen, so just above the screen, okay, just above the screen, at a height h, we have to find out what will be the electric field. Is that correct? So first of all, what is the concept that we are going to use over here? Let me know what should be the concept. Which concept should I apply? Alright, so we are talking about a disk. We are talking about the electric field. Swali says Gauss law. Alright, can you explain how would we use Gauss law over here? Electric field inside a cavity of a conductor is 0. No, swastika. We are not talking about a closed surface. Remember, this is not a closed surface. This is not a sphere. Okay, this is a disk. It's a two-dimensional object. It is not a closed surface. Alright, so we can't really use Gauss's law over here. Okay, that the concept you are telling is certainly used when we have metals or we have spheres with cavity. There we have to use, when we are using metallic spheres with have cavity, there we have to use Gauss's law. No other way to do that. But here this is a disk. This is a simple disk which has a hole in concentric hole. Alright, electric field at circular ring on axial point. Yes, Ayush is getting somewhere. I like that. Electric field on the axis of disk concept. Yes, Azim, that's what I was looking for. Okay, now we have so many different shapes for which we had to remember. We have to remember the electric field due to those shapes. Okay, there is no way around it. We have to remember. So the electric field due to point charge, the electric field due to a disk, the electric field due to a ring, okay, the electric field due to a hollow sphere, the electric field due to a solid sphere. All these things we'll have to remember. There is no other way, okay. So if we talk about a disk, okay, I'm going to give you a simple formula to remember for a disk, okay. Now if this disk has a radius r, then let's talk about a point at a distance of small r, okay. On the axis of the disk at a distance small r, the electric field here, if this is, let's say, positive charge and sigma is the charge density, then the electric field obviously by symmetry is going to be away and it is going to be along the axis. But how do we remember it? We remember it like this, okay. Join this with the periphery of the disk, okay. Join it with the periphery of the disk and let this angle be theta. Can we do that? Then the electric field comes out to be sigma upon 2 epsilon naught into 1 minus cos theta. Now there are a lot of different different ways of remembering this method or remembering this formula, but I have seen that this is the best and easiest way to remember this formula, okay. So the electric field would be sigma upon 2 epsilon naught into 1 minus cos theta. Is that correct? Okay. Now for this disk, all what we are talking about, H. So SVM is asking, can you show where is H in this ring, okay. So I'm going to make a side view, okay. I'm going to make a side view. So this is the disk, okay, it has a hole and this is the axis. So this is H. Can you see that? This is H, okay. So this is basically a point on the axis and we have already figured out what is the electric field due to a disk on the point on the axis. Is that correct? First tell me if this is clear, if the electric field due to disk is clear. And if you really want to calculate it, it's very simple. Again, you'll have to use integration. You'll have to break this disk into small rings, find out the electric field due to ring and integrate that, okay. That way you're going to arrive at the same result. Alright, is this clear? The electric field due to a disk. Now you are going to go home and you're going to write down the electric field due to all kinds of charge configuration. Disk, ring, shell, point charge, everything. Okay, whatever is related, you're going to write down what is the electric field due to those charge configurations. Okay, it is absolutely mandatory to remember them. Alright, perfect. Now that we have done that, then the thing here is, now we don't have a complete disk over here, okay. So there is another twist in this question. We don't have a complete disk over here, okay. There is some part we have removed, okay. So from the complete disk we have removed some part. Is that correct? Okay. So here we can again use superposition, okay. We can use superposition. How do we use superposition? Let's say this disk was complete, okay. Let's say this disk was complete and the electric field due to this complete disk, I'm calling it E complete. Okay, so the electric field due to this entire disk, suppose there is no hole inside, okay, this entire disk, I'm saying that that is the electric field E complete, okay. Now this disk is made up of two things, okay. One is this disk here, which we are going to remove, and the other is this remaining disk with a hole. Is that correct? Okay. So can I say that this electric field due to the complete disk is equal to electric field due to the removed part plus electric field due to the remaining part? Can you say that? Okay, should I write it completely? Remaining, electric field remaining. Is this clear? Okay, so this entire disk, we have broken this into two parts. One is this disk, okay, which we are going to remove, and the other is the disk which is left over here, this disk over here, okay. So we can write that the electric field complete is equal to electric field removed plus electric field remaining. Is that correct? Perfect. If we can say that, then what do we have to do? The objective here is to find out what is the electric field remaining. And what will be the electric field remaining? Electric field remaining would be the electric field complete minus the electric field removed. Do you agree? So all we have to do is we have to find out the electric field due to the entire disk, and then find out the electric field due to the disk we have removed and take a difference of that. Is that correct? Okay, this is principle of superposition in action. Is that clear? Okay, so Swastika is saying we will calculate E due to the complete disk and then subtract E due to the smaller disk. Spot on. Yes, that's exactly what we are going to do. Is that correct? Alright, so let's do it for complete. Let's find out E complete. Okay, so what is the electric field due to the complete disk? This is sigma upon 2 epsilon naught into 1 minus cos theta. Now what we have to do is we have to find out cos theta. So this is the disk. This distance is h. And what is the radius? The radius is 2a. Obviously, I'm talking about the complete disk. Okay, so h is the distance on the axis from the center. 2a is the radius. What angle is theta? This angle is theta. Do you agree? So how do I find cos theta? Very simple. This distance here is going to be 2a square plus h square under root. Do you agree? Simple Pythagoras theorem. Now from here, can I find theta? Cos theta? Of course. Cos theta is going to be h divided by 2a square plus h square and the under root of that. Do you agree? So the electric field due to the complete disk is sigma upon 2 epsilon naught into 1 minus cos theta. Cos theta from this diagram is very clear. It is h upon 2a square plus h square under a root. Is that correct? Okay. Now what we have been given? We have been given that h is much less than a. Okay, h is much less than a. Let's do the approximation over here and get rid of h. Can we do that? Of course we can do that. So this becomes sigma upon 2 epsilon naught into 1 minus h upon this h square we can neglect with respect to 4a square. Is that correct? So what we are going to be left with? We are going to be left with 2a. Do you agree? Okay, so this is the electric field after using the approximation. Now can we calculate what is the electric field due to the removed part? Now the electric field due to the removed part, so what is the difference that is there? This radius is going to become a. So this is going to become a square plus h square. Is that correct? So this removed part has a radius of a. So all we have to do is replace it by the correct quantities. Okay. So this is going to become sigma upon 2 epsilon naught, and the brilliant and the most important thing that happens because we use this formula is that sigma is same. We don't have to consider the charge because sigma is going to be the same for the removed part as well as the entire part. We don't have to worry about sigma. If we do it in terms of charge, then we'll have to calculate charge. That will be a little bit of pain. So that is why using sigma is the best way in this particular method. Okay, so this is going to be 1 minus h upon, and what is the radius? Here 2a was the radius. So what is the radius here? A is the radius here. So this will come like this. Is that correct? Okay, now all we have to do is this remaining electric field remaining. Now remember that the electric field due to both these, so this E complete and E removed, okay, E complete and E removed, both will have electric field in the same direction. So we can simply subtract that. So when we subtract that, sigma upon 2 epsilon naught we can take common, and then this one and this one will get cancelled, and then we'll have h by a minus h by 2a. So this is going to become h upon 2a. So what will be the final answer? The final answer is going to be E is equal to sigma upon 4a epsilon naught into h. Is that correct? Alright, so we have found out what is the net electric field, and this we have to compare with CH. So it's simple to see that the value of C is going to come out to be sigma upon 4a epsilon naught. Is that correct? Okay, so two very important concepts we have used in this question. Number one, the electric field due to a disk, and number two, the principle of superposition applied over here. E complete is equal to E remaining plus E removed. Okay. Alright, so I hope this is clear. Let me know what you think about the difficulty level of this question. Meanwhile, I'll tell you that option A is the correct option. A lot of you could do that. That's excellent. Alright, I hope the concept is clear, and you're going to go back and revise the electric field due to all kinds of charge configurations we have studied. Okay, that's very important. Remembering that is important. Alright. What do you think about the difficulty level? All right. Okay. So I hope this is clear. Oh, okay. All right. Probably there was some lag. I was not able to see the ratings. 2 out of 5. 2 out of 5. 3 out of 5. Yeah, I disappeared for a few moments. You guys also disappeared for a few moments. I think there was a bit of lag, but we are back live. So perfect. Yeah. So you can say this was moderately difficult, if you can say, but if you know the concept, it wasn't really difficult. Okay, the important thing was to remember those two concepts. All right, perfect. Now let's go to the next question. All right, so what do we have here? We have a wire of length 20 centimeter. It is bent into a semicircular arc. If two equal halves of the arc were to be uniformly charged with the charges plus minus q, the magnitude of charge is 10 to the power 3 epsilon naught Coulomb. The net electric field at the center O of the semicircular arc would be. Okay, so we have a wire which has a length of 20 centimeter. We have converted that into a semicircle. One part of that semicircle has a positive charge q, the other part of the semicircle has a negative charge minus q, and the magnitude of charge is same, 10 to the power 3 epsilon naught Coulomb. We have to find out what is the electric field at the center. Alright, electric field at the center. First things first, what is the concept we are going to use? Alright, some people are saying difficulty level 3 by 5, some people saying 40% difficult, medium level, 4 out of 5. Yeah, it was medium level or maybe moderately difficult. Okay, if you don't remember the formula, then certainly it would be difficult. So remembering electric field for all charge configurations is absolutely important. I'm not a fan of memorizing things, but for this one, I'm going to say you have to memorize. Okay, and it's not that you have to take up a book and memorize. This is how you remember things. Okay, we solved a question. You could not solve that question, or you found out difficult to solve this question. So we did that. You're going to go back, revise, and that's it. Okay, you're going to remember it very well after this class. That's how we do revision, right? All right. So what is the concept we're going to use over here? Electric field at the center of a ring. Okay, so what do we have here? We have an arc. Okay, so a ring, a semicircle or a quarter circle, all these things are arcs. Okay, so what we're going to do is we're going to see the general method of calculating the electric field. So let's say we have an arc. Okay, now this arc is subtending an angle theta at the center. Then if this is a uniformly charged ring, let's say it has a charge density of lambda. Here what is lambda? Lambda is charge per unit length. Lambda is charge per unit length. Okay. Then in this case, what is the direction and magnitude of electric field? Do you know that? What is the direction and magnitude of electric field due to this arc which is subtending an angle theta at the center? Okay. So by symmetry we can say that if we draw a perpendicular bisector over here, the electric field by symmetry we can say is going to be in the direction of the perpendicular bisector. It is going to be along the perpendicular bisector. I'm sorry, angle bisector, not perpendicular bisector, angle bisector. So if it is a positive charge, it is going to be away from the charge. If it is negative charge, it is going to be towards the charge. But the thing is, it is going to be along the angle bisector. By symmetry, we can very well say that. Do you agree? And what is the magnitude of the electric field in this case? Let's say R is the radius. Then this comes out to be 2k lambda by R into sine theta by 2. Okay? It is very handy. And I'm going to say this question comes a lot of times that due to an arc, you have to calculate the electric field. So this formula over here comes in very, very handy. Okay, so with enough practice you should be able to remember this. And if you want to derive this, you can do integration and derive this. That's not difficult at all, but we can remember this result in this form. If we remember it in this form, solving this question becomes very, very simple. Okay, so first tell me if this is clear. How many of you knew this in this manner? Electric field due to an arc is 2k lambda by r into sine theta by 2. How many of you knew this? For how many of you it is something which is you are seeing for the first time? Let me know. Swastika says, I have everything written, sir, but not remembered. Of course, Swastika. That's bound to happen. There's so many things that we have written. We're not going to remember everything, and that's exactly why we are doing these sessions. Okay, so after this session, hopefully you'll remember it just a little better. Then you'll do another revision, and you're going to remember it just a little bit better. Alright, I forgot, I knew it. Alright, I absolutely understand that this is something you might have studied, or maybe you have seen it for the first time. So if you've seen it for the first time, alright, here it is, note it down and try to solve a few questions on this. But if you have seen this before and if you are not able to recall it, not a problem. This is exactly what we are doing over here. This is no examination going on. We are discussing so that next time you remember it a little well. That's the objective of this session. Alright, so we are doing what we are required to do. Alright, so this is what we are going to use. So we are going to first take up this positive charge over here. So I'm going to draw the angle bisector, of course. So the force due to this positive charge is going to be in this direction. Do you agree? Along the angle bisector. And if this is the angle bisector, this is going to be 45 degree, this is going to be 45 degree. Do you agree? Alright. Now if this is negative charge, then again I'm going to draw the angle bisector and the force is going to be along the angle bisector. Now the situation is absolutely symmetrical, so the magnitude of force by both the arcs, both the quarter circles, is going to be the same. And if it is going to be the same, then the net force is going to be in this direction. Do you agree? Okay, and what is this going to be? This is going to be 90 degree. The angle between both the forces is going to be 90 degree, and hence we can say that F net is going to be along the x-axis. Okay, so we don't just have to give the magnitude, we have to give the direction also. So this is going to be the direction. So the direction is absolutely clear. So now let's try to find out what is the magnitude. Okay, so along the angle bisector, this is going to be the force, and force we have seen is 2k lambda upon r sine theta by 2. Okay, now this can get a little tricky because r is not given, L is given. Okay, now L is the length. Okay, what is the circumference of this arc? The circumference of this arc is pi r. Okay, 2 pi r ka adha, pi r. Okay, so from here we can say r is L by pi. Do you agree? What is the next thing we need to find out? We need to find out what is the charge density. Okay, what is the charge density? So the charge density, which is charge per unit length. So this positive charge over here, how much is the positive charge? The positive charge is Q. And what is the length? The length is half of the total. So the charge per unit length is going to be Q upon 2L. Do you agree? Okay, I hope that is clear. So we don't want to make mistakes there. We want to do the correct substitutions. Okay, so radius is clear and then lambda is clear. Now all we have to do is do the substitution now. So this is going to become 2 upon 4 pi epsilon naught. So k is 4 pi epsilon naught. Then lambda I'm going to substitute Q upon 2L. Then r I'm going to substitute L upon pi. And then sine theta by 2. What is theta over here? What is the angle subtended? Remember what is theta? Theta is the angle subtended. What is the angle subtended? It is 90 degree. What is half of 90 degree? 45 degree. So sine 45 degree is 1 by root 2. Is that correct? Okay. So this pi and this pi goes away. This 2 and this 2 goes away. So what are we left with? Okay, so we are left with Q upon 4 epsilon naught, and then we have L square. I think, have we made a calculation mistake somewhere? Okay, I was talking about doing the substitution, right? Probably. Let me just check if I've done the substitution right. Okay, so the length is pi r, so the radius has to be L by pi. That is correct. Lambda, oh, I'm sorry, I'm so sorry. Lambda should be Q upon L by 2. I am absolutely sorry. I'm really sorry about this. Okay, so lambda, what is lambda? Lambda is the charge per unit length. Okay, so this has charge Q. I'm just talking about the positive part. So that has a charge Q, and that divided by the length. The length obviously is going to be half. I don't know why I took it double. Okay, so that is going to be L by 2. So this is going to be 2Q by L. Okay, so let me substitute this correctly. So this is going to be 2Q by L. Okay, so what are the things that are going to get cancelled? So this 2 and this 2 are 4. So this 4 is gone, pi is gone. So we are left with Q upon epsilon naught L square and then divided by root 2. Is that correct? So this is F. Now if this is F, then what do we have to find out? So this is also F and this is also F, and they are inclined at 90 degree. So what will be F net? F net is going to be F root 2. Do you agree? F square plus F square, and you know the drill. Okay, F square plus F square under root. Okay, so this is going to be F root 2. So what are we going to be left with? What is the... Alright, I'm sorry, we are calculating the electric field. Why have I written force? Let's write down electric field. That's the same thing. All you have to do is multiply by the charge, you'll get the force. So we are finding out the electric field. Not to worry. So this is the electric field E over here, and this is the electric field E over here. So the net electric field obviously is going to be how much? It is going to be E root 2, correct? Okay, so what is E? E is, let's go back and see what is E. E is Q upon epsilon naught L square root 2. Q upon epsilon naught L square, and then we have root 2. This is the value of electric field, and then we have to multiply it by root 2. So this root 2 and this root 2 gone. This is going to be the net electric field. Now we can do the substitution. Okay, so what is Q? Q is 10 to the power 3 epsilon naught divided by epsilon naught L. What is L? L is 20 centimeter. Matlab 0.2 square. So 0.2 square is going to be 0.04. Is that correct? So this is going to be epsilon naught gone. Then 1 upon 0.04 is going to be how much? 1 upon 0.04 is going to be 25. So 25 into 10 to the power 3 Newton per Coulomb. And what is the direction? Direction we have also already seen. It is going to be along the positive X direction. Alright, so that should be my answer. Ovas says it was an easy one. Yes, if you know the result for the electric field due to an arc, it should be an easy one. Yes, SVM, you're absolutely right. Azim is asking, why not E by root 2? Why would it be E by root 2? Okay, so this is the electric field E, this is the electric field E. What is the angle between them? The angle between them is 90 degree. Okay, so what is that? What is the answer going to be? What is the vector summation going to be? E square plus E square under root. So that is going to be E root 2 or E root 2. Is that correct? Alright, Ovas is asking, sir, are these sessions conducted daily? I think daily we have some of the other live session. If you're talking about physics, then Monday and Tuesday certainly we have a physics session. But I think we have sessions for all subjects. So you can go to the YouTube channel, you can see the schedule there. You should find what is the schedule over there. Alright, but I think more or less every day we have session on one or the other subject. Alright, so difficulty level 3 by 5, 3 by 5. Alright, I'll take that. 3 by 5 or lower. If you know the result, it should be not difficult at all. Alright, perfect. Let's quickly move to the next question. Option D is the correct option. Let's move to the next question. Okay, so here we have 2-point charges plus Q and minus Q. So this is plus Q, this is minus Q. Inside the cavity of a spherical shell. Okay, cavity of a spherical shell. The charges are kept near the surface of the cavity on opposite sides of the center of the shell. If sigma 1 is the surface charge density on the inner surface and Q1 be the net charge on it, sigma 2 is the surface charge density on the outer surface and Q2 be the net charge on it, then these are all the options we'll have to see. Alright. So we have a spherical cavity. Okay, so we have a spherical shell which has a cavity inside. Okay, What they have not mentioned here is, have they mentioned this is metal? They should mention that this is metal. If they have not mentioned, then make a note that this is a metallic spherical shell. Okay, I should write it is a metallic spherical shell. Obviously, then only then this question is going to make sense. Okay, this is a metallic spherical shell. All right. So Mohammed is saying option C. We'll see if the option is C or not C. We'll see to that. Okay, perfect. So tell me what is the concept that we are going to use over here. So sigma 1 and q1 is the surface charge density and charge on the inner surface, and sigma 2 and q2 is the charge on the outer surface. Okay, as in a conductor, the charges inside will be 0. The charges inside will be 0. Not necessarily, Satya. The charges inside need not be 0. It's not a condition. Okay, suppose I take out this charge. Okay, I remove this charge. Then what is the charge inside? The charge inside is q. Okay, so not really. The charge inside shouldn't be 0. So the concept we are going to use here is Gauss's law. And when we are talking about metal, what is it that we know about metal? Okay, the thing we know about metal is that the electric field, yes, electrostatic shielding, exactly, that's what we are talking about, electrostatic shielding. And what is the core concept behind electrostatic shielding? That for a metal, the meat of the metal, the material of the metal, there can be no electric field. Okay, there can be no electric field inside the material or meat of the metal. That is the concept. Okay, so what we're going to do here is obviously apply Gauss's law. So what we do here is we take a Gaussian surface through this metal. Okay, we take a Gaussian surface through the meat of this metal. Why? Because the electric field then through the Gaussian surface is going to be 0. Is that correct? The electric field through the Gaussian surface is going to be 0. Now if the electric field due to the Gaussian surface is going to be 0, then what is the flux? The flux is going to be 0, and hence what will be the charge inside? The charge inside should be 0. Okay, the charge inside the Gaussian surface should be 0 if there is no electric field through the Gaussian surface. That is the concept. Is that correct? Okay, yes, it should be a metal sphere. Absolutely, it has to be a metal sphere. Only then this question is going to make sense. Is that correct? Perfect. So we have chosen the Gaussian surface, and through this Gaussian surface the flux is 0, which means the charge inside has to be 0. Okay, so what is going to happen? We have a charge q here, we have a charge minus q. So what is the charge that is going to come on the inner surface? Okay, the net charge has to be 0. So this charge and this charge over here, q and minus q, gives me 0 charge. Is that correct? So what should be the charge on the inner sphere? What should be the charge here? What should be the charge here? On the inner sphere, okay, inner surface, what should be the charge? Okay, the net charge has to be 0, which means the total charge on the inner sphere has to be 0. So if the total charge on the inner sphere is, or inner surface is q1, then q1 has to be 0. Is that correct? So this is very simple. Q1 is going to be 0, not a problem at all. But the question is the charge density going to be 0? Okay, now notice that the situation is not symmetrical. Now this q and this minus q, it is not placed at the center. They are placed near the surface, which means there is going to be some induction. So this q, this is positive charge. So what is going to do? It is going to pull the negative charge over here. So the negative charge density is going to be higher over there. And this minus q is going to pull the positive charge over here. So the positive charge density is going to be higher over here. Although the net charge is going to be 0, but the charge density is going to vary. The charge density is not going to be the same throughout the inner surface. The charge density is going to vary. And since the charge density is going to be varying, then we cannot say that the charge density is going to be 0 everywhere. Okay, so we will have to say that sigma 1 is not equal to 0. Is that correct? The net charge is 0, but the charge density at different points is not 0 everywhere. Okay, so sigma 1 cannot be 0. Is that correct? So that is clear. What else do we have? We have the outer surface. Okay, again what we are going to use here is, we are going to use for the outer surface, we are going to use the concept where if it is an isolated conductor. Okay, if it is an isolated conductor, the net charge on the conductor has to be what? It has to be conserved. Okay, so we are talking about an isolated conductor, aren't we? So this is not connected to anything. So what is the net charge on the conductor? The net charge on the conductor is plus q and minus q. Okay, so the net charge on the conductor is 0, so the final net charge on the conductor has to be 0. Okay, so we chose a Gaussian surface here. So the charge on the net charge on the Gaussian surface, net charge on the surface on the inner surface, that was 0. This q and this minus q is already 0. So what is the net charge we see inside the Gaussian surface? The net charge we see inside the Gaussian surface is going to be 0. So what should be the charge outside? The charge outside should also be 0. Do you agree? Sir, can you clear in front of question slide, please? Okay, let's do that. If you want me to do it there, not a problem. Let's do it here itself. Okay, so you can see the question also. Alright, so is the first argument clear? Is it clear that why the charge inside this on the inner surface is 0? The charge on the inner surface is 0, but the charge density is not 0 everywhere. Is this clear? Is there any confusion regarding this? If there's any confusion regarding this, let me know. Okay. We have chosen the Gaussian surface like this. Inside the Gaussian surface, the net charge has to be 0. This plus q and minus q is making it 0. So charge on the inner surface also has to be 0. But because this is not symmetrical situation, this plus q is going to pull the negative charges here. This minus q is going to pull the positive charges here. The charge density is going to be non-uniform. And if it is non-uniform, we cannot say that the charge density is 0 everywhere. Is that correct? It is going to be varying at different places. Perfect. Now what we are talking about? We are talking about the outer surface. Okay. Now this conductor has 0 charge. What does it have? It has a 0 charge. Total charge is 0 on the conductor. Okay. Now this is isolated conductor, which means the charge before and the charge after has to be 0. Okay. Now, right now, what is the net charge? The net charge on the inner surface plus the charges inside, that is making it 0. So what should be the charge on the outer surface? The outer surface has to be 0 because the net charge on the entire sphere has to be 0. Is that correct? Clear? Okay. So Q2 is 0. Now what about sigma? What about sigma 2? What is going to be the charge density over here? Now if the charge density, if this Q2 would not have been 0, just assume if this Q2 would not have been 0, then this charge distribution would have been uniform. Why? Because only then this is going to give me 0 field inside the conductor. Okay, so on the outer surface, the charge distribution has to be uniform. Only due to a uniform charge distribution, the field everywhere inside is 0. Is that correct? Okay, so if Q2 was not 0, just assume that Q2 was not 0, then the charge distribution would have been uniform. Okay, but if Q2 is 0, then also we can say that the charge distribution is going to be uniform. So we are going to have 0 charge density everywhere. It is not going to be varying. So every point you take, it is going to have the charge density as 0. Is that correct? So what will be the correct option? The correct option from here has to be option B. Sigma 1 is not going to be equal to 0, but Q1 is going to be equal to 0. Sigma 2 is going to be equal to 0, and Q2 is also going to be equal to 0. Is that correct? Okay, so this is electrostatic shielding we are talking about. And this is there are basically two concepts involved. Okay, you choose the Gaussian surface through the meat of the conductor, then the net flux through the surface is going to be 0, which means the charge inside is going to be 0. And the isolated conductor, for isolated conductor, we are going to get the charge conserved. Okay, for an isolated conductor, the total charge of the conductor is going to be conserved. These are the two concepts we have used over here. Alright, Satya, if Satya is saying somewhat I understand that it's not a very straightforward concept. If you are not able to understand the concepts, then you need to go back and revise electrostatic shielding, because electrostatic is a shielding is a topic which I teach in 3 hours. Okay, I take 3 hours to teach electrostatic shielding. It's a very conceptual topic. So obviously I cannot go a lot in depth because we are revising, but you can always go back and you can revise it, and then it is going to it is going to make more sense to you. All right, very interesting topic, very conceptual topic, and a very important topic as well. A lot of questions are asked on electrostatic shielding. All right, but I hope for the rest of you who are familiar with electrostatic shielding, this was a good revision and you are clear with the concept. Okay, now quickly give me the rating for this question as well while I give you the option. Option B is going to be the correct option. 4 out of 5. If you ask me, I would give it 3 out of 5. It's not absolutely simple, but I'll give it 3 out of 5. But certainly not 4 out of 5 OS, because probably you have forgotten electrostatic shielding. All you need to do is go back and revise, and then certainly this would seem a bit easier. All right, perfect. So let's go to the next question. Let's go to the next question. Okay, so in the interest of time, I'm skipping a question because I don't want to repeat the concept. So let's go ahead with the session, and in the interest of time, we're going to do the most important questions. Okay, so let's get to this question. Now we have a capacitor. A fully charged capacitor has a capacitance C. It is discharged through a small coil of resistance wire embedded in a thermally insulated block of specific heat capacity S and mass M if the temperature of the block is delta T. Oh, so verbose. Okay, blah 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 blah. Too many words. Okay, simple concept is we have a capacitor. It has been charged to a potential difference of V, and then we have a resistor, and this resistor is embedded in a thermally insulated block. Okay, so this blue block you are seeing is thermally insulated. Okay, so it is going to get heat from this resistor, because resistor is going to get heated up. It is going to get heat from the resistor, but it cannot distribute the heat outside. Okay, the heat cannot be radiated outside. It is insulated. So whatever heat is generated is going to be generated is going to raise the temperature. Okay, heat is not going to flow out. That is the question. Okay, so what we have to do is we have to find out what is the potential difference V when the increase in temperature of this block was delta T. Okay, perfect. Let's solve this question. Okay, first of all, tell me what is the concept that we're going to use over here. OVAS says, because I didn't know, sir. And that's all right, OVAS. You can always go back and revise this concept. Not a problem at all. Okay. It is a very conceptual topic, so it will need a little bit of effort to understand that completely. Okay, so that's what we are doing over here. Now you know that this is a weak topic for you. Okay, so just go back and revise it. That's all we have to do. Okay, so what is the concept involved here? Very simple. The capacitor is going to get discharged. Now if the capacitor is going to get discharged, the current is going to flow through this resistor. The resistor is going to get heated up, and that is going to increase the temperature of the block. That's all. Okay, so what is basically going to happen is how much heat is going to be produced. Obviously conservation of energy has to take place. Now what is the energy of the capacitor? The potential energy of the capacitor is half CV square. Is that correct? Potential energy is half CV square. Now when the capacitor is completely discharged, all this energy is going to be lost. Okay, the net charge is going to be 0. So all this energy is lost, and it is going to get converted in what form? It is going to get converted in the form of heat. Do you agree? Okay, and what is the heat that has been taken up by this body? It is going to be ms delta T. Is that correct? ms delta T. The heat it has taken, the heat it has absorbed, this body is going to be ms into delta T. Okay, so whatever is the loss in potential energy of the capacitor, that has been converted to the increase in temperature of this body. So we're going to get V is equal to 2 ms delta T upon C and the under root of that. Is that correct? Alright, a fairly simple question. Alright, what should be the correct option? The correct option should be option D. Most of you are right. So let's, and I know the difficulty level for this is going to be something 1.5. So I'm not going to ask you. It's a fairly simple question. But let's go ahead with the next question. Alright, so what do we have here? We have a parallel plate capacitor with a dielectric constant K. Between the plates has a capacity C and is charged to a potential difference V. The dielectric slab is slowly removed from the plates and then reinserted. The net work done by the system in this process is. Okay. Azim is asking, S is specific? Yes, S is specific heat capacity. Alright, so we have a charged capacitor. It has a potential difference V. There is a dielectric slab with dielectric constant K. Now this slab is taken out and it is reinserted. What is the work done by the external force? That's what we need to find out. Alright, so quickly tell me what is the concept involved in this question. I'm going to wait for this one. Alright, 0. D. Let's see. Before we jump to the question, let's talk about the concept. What is the concept involved over here? Dielectrics. Satya is saying dielectrics. Yes, definitely we are talking about dielectrics, but you need to be a little more specific. What exact concept of dielectrics are we talking about? Your answer is absolutely right, KRPE. Your answer is absolutely right, but I need the concept. What is the concept that has been used over here? That's the important thing. Work done is equal to QV. Work done is equal to QV. That's, I think we're talking about battery in that case. Charge flown the battery, dielectrics will increase the capacity. Yes, the dielectric will increase the capacity. Charge flown through the battery. Charge flown through the battery and work done by the battery is certainly a concept that is involved over here. Okay, so I don't have the time for the derivation, but remember this. Okay, I don't have the time for derivation, but I'm going to give you the result. Okay, you can always go back and see the derivation. Now, if we have a dielectric inside a capacitor, then there is a constant force on it. Okay, what is this constant force? This constant force is epsilon naught BV square into K minus 1 upon 2T. Okay, I'll ask you to go back and revise this concept and see how it was derived. I don't have the time to do the derivation. I'm directly going to give you the result. The force on this dielectric is epsilon naught BV square K minus 1 upon 2D. What is B? B is the width of the capacitor plate. Now L is the length of the capacitor plate. It is going to have some width. That width is B. Okay. What is V? V is the potential difference, K is the dielectric constant, and D is the distance between the plates. Okay. This is the result. Now the important thing is that this is an attractive force. This force is always an attractive force, and this is constant as well. Okay. So this is an attractive force which is constant. So force F is being applied over. The electrostatic force on this dielectric is like this. Okay, so when we are taking it out, the work done is going to be by this electrostatic force. The work done is going to be negative because force is towards the left and the displacement is towards the right. Okay, so the work done in this case, when we are taking out the slab, the work done is going to be negative. But when we are reinserting the slab, the work done is going to be how much? The work done is going to be positive. Okay. Since the magnitude of force is same and the displacement is also same, so the work done in both the cases are going to be the same. But one is going to be negative, the other one is going to be positive. So the net work done is going to be 0. Is that correct? Okay. So in this case, the net work done is 0, which means my answer has to be 0. Is that correct? So the net work done by the system in this process is going to be 0 because while taking out and while reinserting, the work done has been equal in magnitude, but one has been positive, the other one has been negative. Okay, but the important thing is this concept. Okay, there are direct questions asked on this concept in JEE. Okay, so do remember this concept. All right, perfect. Let's move to the next question. All right, so this is the last question we are going to do today. So what do we have? We have a simple pendulum of length L. It is placed between the plates of a parallel plate capacitor of electric field E. Its bob has a mass m and charge q. The time period of the pendulum is given by. Okay, so simply there is I'm sorry, inside a parallel plate capacitor we have a pendulum. Now this pendulum, will this pendulum stay vertical? So Azim is saying, sir, if it is not constant, then it would not be 0. It depends, Azim. It depends. If it's a symmetrical situation, then also it can be 0. Okay. If the force at every so if the force is, so this is an electrostatic force. Okay, and electrostatic force is conservative in nature. Okay. So if the electrostatic force is conservative in nature, then in a round trip the net work done has to be 0. Okay, so even if the force was not constant, even then it would have been 0. But the main concept here is that on the dielectric, which is placed inside the parallel plate capacitor, the force, the electrostatic force, is constant and attractive. Okay, it is always attractive. You take it to the left side, the force is going to be on the right side. You take it to the right side, the force is going to be on the left side. Okay, now in this case, the question we are dealing right now. Now in this case, can you tell me, is the pendulum going to be vertical in its equilibrium position? Is it going to be vertical in the in the equilibrium position? Is this pendulum going to be vertical? No, obviously not. Okay, why not? Because there is an electric field inside between the plates of the capacitor, and that is going to apply a force. So we are going to have a situation which is something like this. Now this is mg and this is QE and this is tension. Okay, this is going to be the equilibrium position, and from this equilibrium position, if we displace it slightly, it is going to perform an SHM. And what will be the time period of this SHM? Okay, can someone tell me what will be the time period of this SHM? How do we go about it? What is the main concept over here? So do you remember those kinds of questions where we have a trolley and then this trolley is moving with an acceleration of a0, and then we have a pendulum, and this pendulum makes a certain angle with the vertical, and then if we displace it slightly, it performs an SHM. Okay, does it ring a bell? We have seen this situation in many places. Okay, alright, so if you have forgotten, don't worry, I'm going to revise it. Okay, so what we are going to do is we're going to find G effective. Okay, we're going to find G effective. How do we find G effective? In the equilibrium position, T will be equal to mg effective. Okay, in the equilibrium position, the tension in the string is going to be m into G effective. Is that correct? Okay, so we have a force mg over here, we have a force QE over here, and we have tension. Now this is equilibrium position. If this is equilibrium position, then all the forces should add up to 0. Is that correct? Okay, so if I add up mg and QE, that should be equal and opposite to tension. Is this concept clear? If I add QE and mg, this should be equal and opposite to tension, because all the three forces together are going to give me 0. Is that correct? Okay, so the angle between mg and QE is 90 degree. So the net force here is going to be how much? It is going to be QE square plus mg square and the under root of that. Do you agree? That is going to be the net force. Okay, so that is going to be the resultant of mg and QE. Okay, now this force over here has to be equal and opposite to tension, because the net force has to be 0. Is that correct? So the situation is something like this. We can say this is equal to m into g effective. Okay, the situation is something like this. So now what I want you to imagine is that our world has become inclined. Okay, now what I want you to imagine is, let's say our world has become inclined and you are going to be like this. The world has just inclined, okay, where the direction of gravity and the magnitude of gravity has changed. Okay, suddenly this has happened, and what you're going to see is something like this. Now I want you to imagine that the world has become inclined and you're going to observe the world in an inclined position. Okay, you're going to observe the world in an inclined position. Okay, now what used to happen in the normal world? You used to observe the pendulum like this. Is that correct? Okay, then this was mg and this was tension, so you said that the time period is 2 pi under root of L by g. Is that correct? In a normal world, you used to say that this is the time period. Okay, you used to watch the world in this particular orientation. Is that correct? So in that case, in the equilibrium position, T was equal to mg. But in this situation, what has happened? T has become equal to m into g effective. Okay, and all that has happened is our world has become a little inclined. Okay, but should that be of any problem? Okay, should that be of any problem? So in this case, we used to use T is equal to 2 pi under root of L by g. Now in this case, the time period will become 2 pi under root of L upon g effective. Is that correct? Okay, so all we have to do is, we have found out m into g effective, which has this value. So all we need to do is, we need to substitute g effective in this particular equation for the time period. Okay, so T should be equal to 2 pi into under root of L upon g effective. And what is g effective? G effective is going to be this quantity divided by the mass. Is that correct? Now I'm running short of space, so I'm going to rub this off and I'm going to give you the final answer. Okay, so the time period should be something like this. Okay, all you need to do is find g effective and substitute it into the equation for time period. Is that correct? So that should be our answer, and this is not just restricted to electrostatics. So you will find this situation in a lot of problems. Okay, you'll find this situation to find the time period of the pendulum in different situations. Okay, here we had electrostatic force. Tomorrow we can have a pseudo force. We can have any other constant force. It could be a number of forces acting, but the concept remains the same. Okay, you find T is equal to mg effective in the equilibrium position. And once you have found out g effective, then all you have to do is substitute for 2 pi under root L by g effective. That's it. That's how you want to do it. All right. Perfect. So I think that's it for this session. We have discussed some very interesting and extremely conceptual questions for electrostats, capacitors, Gauss's law. These are very conceptual chapters, and it's important to revise them frequently. All right. So I hope this session was helpful for you. Let me know what other sessions you want, what are the chapters which are really troubling you, and we are going to get back to that. All right, we'll try to incorporate all those problem areas for you. All right, so I'm going to see you very soon. Till then, keep practicing, keep getting better, and have fun with learning. All right, so last question, I think Satya Bharat is asking, so how will be JEE, difficulty? Nobody knows, Satya. JEE 2022, what is going to be the difficulty level? Nobody really knows. And it does not matter, because the competition is going to remain the same. The number of people who are appearing for this exam is going to be the same. So be it higher difficulty, lower difficulty, does not matter. You need to be at your best. That's all I can say. All right, so that's it for this session. See you very soon, and thanks a lot for watching.